Now I said valence bond theory and VSEPR give us the exact same results. But the book only mentions sp3, sp2, and sp hybrid orbitals. And that covers geometries where we have a total of 4 bonding regions. But in VSEPR, we also saw that we had 5 and 6 bonding regions in some cases. You may remember that we said we can have our trigonal bipyramidal, so we have something pointing upward, 3 along an equator, something pointing downward. We also said we can have our octahedral geometries where we have bonds there, 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 and there. So 5 and 6. How do we get to that point? Well, I just wanted to show you something from outside of our book that'll help pull this together a little bit. And I'm not going to worry about showing this geometry. We're going to focus on the octahedral geometry for a moment. We can actually go ahead and take some d orbitals as well and mix in electrons, or at least mix in the regions of space for the d orbitals, and get hybrid orbitals that include the s's, the p's, and the d's. So in the most complicated case here, we take our s orbital, all 3 p orbitals, and 2 d orbitals. And we're going to mix those together. We're going to leave 3 of the d orbitals totally alone. Notice that we've got 1, 2, 3, 4, 5, 6. A total of 6 orbitals that we're mixing, which means that there's going to be a total of 6 orbitals that we're making. How convenient that there will be 6 areas that we can have bonds made. This will tie back to that set of geometry as well and match up with our AX6 geometry family. Now here's exactly why. Suppose we have a sulfur atom, and right now it's all by itself. There's no fluorines around it. So that means we go ahead and fill in our valence electrons. We have our 2 s electrons. We start filling in our p electrons. Now remember, sulfur and oxygen are in the same group. We had a total of 6 valence electrons to fill. Here's 2 of them. 3, 4, 5, then 6. We always follow Hund's rule and fill them one at a time. We end up having our d orbitals, and those are still completely empty because remember, we'd have to go to the periodic table. Right here's sulfur. We'd have to come all the way around. Actually, I should have dipped that down a little further. There we are. Just ignore this. We'd go around the periodic table, fill up all of our 3 p's. Then we'd fill up our 4 s's. Then finally we'd start putting electrons into our 3ds. So these 3ds are still completely empty, but they still exist in space, and they still have certain energies to them. Now notice that if we were to take those energies and mix them all together, if we only had one of these, they'd end up being pretty much the same as the p orbitals. This is going to be slightly higher in energy than the average of our 3s and our 3p's and our 3d's. So yeah, we do have to put in just a little bit of energy, but hopefully we get enough stabilization by actually building the whole molecule that it ends up being worth our while. Now you see that we end up with those 6 hybrid orbitals. Each one has a single electron in them. Fluorine, of course, has 7 electrons, it being a halogen. If it pairs up to make a single bond, then each of these will end up being filled. And so it'll be, perish the word, happy, and be very stable. So sulfur hexafluoride should be a fairly stable molecule based on this sort of an approach. Now, of course, you might say to yourself, okay, great, sulfur hexafluoride. This sounds like something that, I don't know, we're probably never going to deal with. This seems pretty exotic. And, well, yeah, you're probably not going to encounter this in everyday life. But if you do feel like encountering it in an amusing way, just go ahead and hop over to, let's just say, your favorite video site. Go ahead and type in Mythbusters, helium, and sulfur hexafluoride. It's got a pretty amusing video where you get to hear him inhale some sulfur hexafluoride and also inhale some helium. My point with that is it's a stable molecule. Not only that, but it's not very reactive, as evidenced by the fact he could have it in his lungs and not die. It didn't react with the water or the tissue inside of his lungs. It's not recommended that you try the sulfur hexafluoride experiment because it's really dense, and so it's very hard to get out of your lungs. It's almost like you've got, I don't know, liquid that you can't use. Well, fluid you can't use, in fact. Kind of like having water in your lungs. That's a fluid you can't use to inhale any oxygen either. Well, sulfur hexafluoride is going to be a gaseous version. It's still going to be a fluid. Luckily, it's not going to harm you. It's just going to be blocking a lot of the oxygen from getting in your body. So you'd have to make sure that you kind of work it out of your lungs pretty quickly to make sure you can continue breathing. Otherwise, you could suffocate in your own lungs. So I just kind of wanted to give you that quick little tangential aside. And sulfur hexafluoride will probably come up again in a few of our chapters later on when we talk about the gases, because it's a really neat gas when we talk about dense gases and our ideal gas law.